Okay, our next keynote is going to be three executives from representing FADU. First is going to be Eric Spanneut, who is Vice President of Flash Global Product Management at Western Digital. In his role, he's responsible for the company's enterprise SSDs, client SSDs, eMMC, and UFS product portfolio. Prior to Western Digital, Eric has management roles at Honeywell, Micron, and Samsung Electronics. Eric earned his master's in electrical engineering from Telecom Paris Institute of Technology and an MBA from INSEAD. Next is going to be a customer in this presentation, Ross Stenford, who's a member of Meta's storage hardware team. He has over 20 years of experience developing and bringing leading-edge storage products to market. Ross works very closely with industry partners and standards organizations, including the NVM Express, SNIA, and the Open Compute project. With experience including ASIC design, he has an appreciation of design challenges facing the SSD providers and how to enable solutions for performance and quality of service with a shrinking power envelope. Ross holds over 40 patents. Along with the two of them, we're honored to have back Anu Murthy, who's VP of Marketing for FADU. She's worked since 2005 in the flash industry at Samsung, SanDisk, Kioxia, and Seagate, in a variety of roles from architecture, technical marketing, strategic marketing, and product marketing. At FADU, she's led their business development and marketing since 2019. She brings a wealth of experience and has an MBA from the Haas School of Business, Berkeley. Welcome, FADU.
Okay, good afternoon, everyone, and thank you for joining this session. So the enterprise SSD space has been going through a deep transformation, and in just 30 minutes, you're going to be hearing 3 points of view from a flash vendor, from a controller vendor, and also from a hyperscaler. So I will first explain the transformation and challenges, then Ross from Meta and Anu from FADU will come on stage to address the opportunities. So enterprise SSD has become a key component of has become a key component of the data center infrastructure. And this year, the demand for enterprise SSD is expected to grow by a staggering 70%. And what a change from 2 years ago, when the market was signaling a slow migration to higher cap, slow transition to PCI Gen 5, and overall a sluggish demand. So in the past 5 years, the disaggregation of compute and storage in the cloud has led to a bifurcation of the enterprise SSD offering, with essentially two classes of enterprise SSD. You have the compute enterprise SSD, and second, you have the storage enterprise SSD. So the compute enterprise SSD, they reside in the compute clusters. They handle mission-critical workloads. They tend to be lower in capacity. They tend to move faster to the latest NVMe interface. And they really differentiate through a combination of high endurance, low latency, and strong performance, especially the mixed random read-writes. On the other hand, the storage enterprise SSD are really foundational to the modern hyper-converged scale-out architecture. They are typically present in large object stores or data warehouses, and they are larger in capacity than the compute enterprise SSD. They are slower to adopt the latest NVMe interface, and they present a more balanced approach to cost, power, and performance and endurance. So the recent surge of AI workloads has added new requirements to both class of enterprise SSD, as enterprise SSD participate in most stages of the AI pipeline. The compute enterprise SSD are co-located with the GPU. During the training stage, they provide an additional layer of cache on top of HBM and DRAM. They store snapshots of the model under construction. And during the inference stage, they enable RAG, or retrieval augmented generation. So these drives need to be super fast on the read and write side, and AI is really accelerating their transition to newer NVMe interface. Now, storage enterprise SSD are a key constituent of those fast data lakes from which the models get trained. During the AI data preparation stage, they play a key role in the ETL, or extract transform load process. And here, AI is pushing to the need for higher capacity that combine good enough performance with an acceptable TCO. So overall, AI represents a fantastic opportunity for the enterprise SSD market and for NAND in general. And our models predict that an additional 150 exabytes of demand will be created in 2028 just because of AI. AI is also disrupting the enterprise SSD demand by mixed by category of servers. So you have the quick rise of a new category of AI server that mostly benefit the compute enterprise SSD, and quick growth of the average capacity per storage server, which benefits the demand for storage enterprise SSD. So this opportunity, however, is not without presenting some challenges. We don't have time to cover all of them, but the first that comes into mind is the form factor, as we are looking at an explosion of form factors in that space. So capacity, thermal, real estate are critical decision criteria for deployment. Ross will be highlighting here a hyperscaler perspective in just a moment. The second challenge is advanced data placement to address the write amplification issues and prolonged life cycles and enhanced TCO. So as FDP seems to be gaining the most traction in that space, so Ross again will cover the recent developments around it. Maintaining fleet at scales as the fleet sizes continue to increase. So what's the latest on telemetry and debugging, debugging capabilities? Reducing qualification time. What are the new initiatives, especially around testing? And finally, PCIe transition. So can the industry support accelerated migration to new interfaces? So Anu will touch on that topic later in the presentation. So let me just pass the baton to Ross, who's been patiently waiting to present some of his solutions. Thank you very much.
Thank you very much, Eric. So we'll start off with my lawyer's favorite slide, and now let's continue and get started here. Let's talk about some hyperscale perspectives. We heard questions about form factors, so let's start off with form factors. Where are they going? So E1S, let's assume 8 placements, 32 die stacks. If you have 1 terabit dies, you do the math, 32 terabytes. If you have 2 terabit dies, it takes you to 64 terabyte capacity. You have 4 terabit dies, it takes you to 128 terabytes. As you can see, the capacity scales very well with time and with die sizes. It's doing very well. 128 terabytes and higher, there's some challenges, and we'll talk about that in a minute. The other question is, well, how is E1S doing in the marketplace? Well, let's look at our form factor trends here. You see 2021 at 2%, 2023 at 17%. It's almost 9x in a very short amount of time. Go out to 2028, you will see 51%. So as you can see, we could talk about densities, thermal, power, security, all the benefits of E1S, but it meets the market needs. That's the only way you have this kind of growth. Now, high capacity. Let's talk about some of the considerations here. First one is, what is the max capacity requirement? We've heard a lot of things today. Our customers are saying a lot of things, but what is it? When we evaluate it, you say, okay, well, let's look at the number of NAND placements. Well, quickly, is that a standard package you're looking at? Are you using a custom package? Do you assume 4 terabit timelines? Do you assume 16 or 32 dies per package? A lot of questions in this space. Next thing, performance. Say, yeah, performance matters. Well, once you figure out what your performance is, how much power do you need? What should the indirection unit size be? Should the FTL be in DRAM or NAND? As you can see here, there are a lot of considerations, lots of questions. You know, I think we'd all agree, you know, we want unified industry form factors. We don't want fragmentation is bad for the industry. It's bad for customers, it's bad for suppliers, it's bad for everybody. And so my call to action here is we need to start talking. We need this about what do we want? What do we need? What are the requirements? And we don't have to, but the result of that will be fragmentation, and it'll be bad for all of us. With that, let's keep going here. We talked about data placement, so let's talk about flexible data placement. Where is this going? It was ratified December 2022 at NVMe Express. 2023 is FMS's winner for most innovative memory technology. It improves endurance, performance, quality of service through data placement. Key adoption drivers with this. It's low development effort with high benefits. It's backwards compatible. Applications don't have to know FTP to get benefits. They can benefit without FTP. Applications that understand FTP obviously have higher benefits. Open source. Open source is key in growing ecosystems and everybody being able to use this. You know, Linux kernel I/O pass-through is complete. For the Linux kernel, lifetime hints is something in progress. Then we can go through XNVMe, QEMU, FIO, NVMe CLI, CacheLib. These are all open source efforts that are complete. You can go download them while you sit there in your chair today. It's available now. Now, let's talk about the OCP data center NVMe spec and give an update on that. Start off in 2019 with Meta and Microsoft. Then the version 1.0 came out in 2020. 2021, Dell AMC and HPE joined the effort. The 2.0 version came out. 2023, Google joined the party for version 2.5. Version 2.6 is coming. What's great about this spec, it has learning from all these customers who deploy at scale, large engagements. All the problems we struggle with, our learnings flow into this spec. What that means is it enables management at scale. There's monitoring, debuggability, whether it's a health information extended log, what goes in there, all the problems we've experienced that others are going to experience so that we can manage things at scale. the latency monitoring feature, the human-readable telemetry feature. This is all about management at scale and being able to make things work. And not only that, there's open source tooling. There's OCP NVMe CLI, sits on GitHub. You can go download that today and use it to manage your OCP-based drives. So what does this spec enables? It enables more features, better quality, and faster time to market. And that's a very unusual combination. Usually you can get one of these. You can always get one. It's hard to get two, but it's very unusual to get all three of these things. So this really benefits the entire industry, and we're looking forward to getting version 2.6 out. Now, something else new for 2024. You know, time to market is everything. How do you left shift? And what do we have now? We have open source qualification test cases. What that means is test cases are used in qualification today. They are open source. You can download them today. You can run them. And this effort is going to continue to grow. The question I would ask is, why would you not run the open source test cases? It improves development and qualification timelines. So lastly, let's talk about open flash innovation. We got 2018-19, we got the E1S form factor with enclosure and heat sinks, improved signal integrity, thermals, power, security, density. Then 2020, 2021, we had the OCP NVMe specification, aligned hyperscale and enterprise to a single specification, add latency monitoring out of problems of how do you manage drives at scale. Then 22, 23, flexible data placement, improves endurance, performance, QoS through placement. 23, we have telemetry and debug improvements. They're defined in the OCP 2.5 spec. You can download it today and take a look at it. Accelerates debug, time to market. Enables management at scale. 2024, now we have open source SSD test cases. Accelerates development qualification times. That's good for all of us. So what's the takeaway from this slide? What should you take away? You know, collaboration on real-world problems leads to great ideas, resulting in great products. So with that, thank you very much.
Hi, let's talk about SSD controller perspectives. My name's Anu. I'm VP of Marketing at FADU. The AI infrastructure coming in has put huge demands on the infrastructure, and the SSD industry needs to respond to it, as well as the controller needs to support the SSDs to meet the demands of AI. So what are the AI infrastructure demands? AI infrastructure growth today is greatly constrained by the total power available or generated in the US, and is also very scarce elsewhere. GPUs are extremely power hungry. So can we reduce storage power and maintain the performance needed? Can we enable the shift from HDDs to large capacity SSDs to reduce power, as well as enable cooling and TCO? The other change that is happening due to AI infrastructure is major product updates happen every 2 years. That means the pace of innovation has to be greatly increased. Can we maintain the pace of innovation and scale performance requirements, which are scaling with the AI for snapshotting and recovery? Can we have the right architecture to add new features easily? Do we have the right business model to enable the pace of innovation? Let's take a look. FADU came to fame in 2019 with our breakthrough architecture, which gives you the highest performance with very low power. We've continued this trend through Gen 3 to Gen 4 to Gen 5. Let's see how we're doing in Gen 5 against the leading competition. As you can see, on all 4 corners of sequential read, sequential random read, and random write, we've shown of power from 36 to 49% more than the leading competition. This is unprecedented. Let's see how that power savings translates to TCO in a system. At the bottom of it, you can see 2 systems that we create with 1 server, fan, and 24 E1S SSDs. In one of the systems, we have FADU SSDs. In the other one, we have leading competition SSDs. And by server, we mean CPU, DRAM, NIC, motherboard. As you can see, the system power has about 25% savings by using FADU SSDs as compared to the leading competition. This translates to TCO savings of 29%, which includes CapEx and OpEx costs. So FADU Gen 5 controllers have been shipping since 2023. We have the highest performance controllers in the industry, supporting up to 14 gigabytes per second of sequential write, 10 gigabytes per second of 14 gigabytes per second of sequential read, 10 gigabytes per second of sequential write, 3.3 million IOPS, and a whopping 500K IOPS of random write at the lowest power seen of less than 6 watts at full performance. We support full drive level security and reliability and comprehensive features such as FTP, OCP 2.5, Advanced NVMe 2.5, SRIOV. This is the controller that's powering the advanced WD SN861 series recently announced, the best SSD in the industry today. We always lead in following all the standards in the industry, and it's served us really well. FTP is a great example of that. As you can see by FTP, you can see here that there's a mixed workload bandwidth, and by using FTP, we can see increases in performance up to 91% from 51%, ignoring the noisy neighbor problem, and this has served us well in terms of our performance leadership. What makes FADU so good? How can we repeatedly show the best performance per power? The secret is with our hardware-software co-design. The hardware-software co-design enables a very efficient pipeline that's hardware-accelerated but flexible. This enables us to run not just the controller, but the NAND as well as the DRAM at the right speed for performance. This gives us the lowest power for performance that scales well from generation to generation. It also helps us with flexibility and time to market. So if we need to spin a new firmware feature quick, we can use this design to do it. It's also easier for us to rip chips. This helps time to market. As Ross talked about it, everybody is talking about transition from HDDs to large capacity SSDs to enable TCO. What can a controller do to enable it? We will support large variable page sizes, support for low DRAM, DRAM-less SSDs for low costs, and support for low capacity SSDs. We're also watching the standards very closely on this front. So we hope you guys come up with a good standard quick, so we can support it in our next controller. Introducing Sierra. As you can know, the Gen 6 infrastructure is coming up. It's right around the corner. We're introducing our Gen 6 controller, Sierra. It's got a whopping 28 gigabytes per second of read and write, maximizing the PCIe 6 bandwidth, and we'll have 6.8 million IOPS. We support both types of virtualization, physical as well as virtual. We'll support physical functions as well as SRIOV. We support confidential computing and quantum-safe security. We'll support capacities up to 256 gigabytes. And all this while we double our power efficiency. So we're pretty much the leader today, and in the next generation, we will double our power efficiency. So we are pretty sure we'll be the highest performance, best power solution in the market. Our samples will be in 2025, and we'll be shipping in late 2025. We also try to rev the business model, because in the past, we had two forms of business models for controller vendors. The controller vendors would do the chip design and validation and an SDK, and they'd throw it over the fence to the SSD makers, who then do firmware development, validation, system validation, and CJQ. Now, this has certain advantages, because the SSD vendor owns the code as well as the SSDs. And large OEM vendors and hyperscalers have one throat to choke if something goes bad. But it's a really long time to market. It really does not serve the AI infrastructure changes really well. We had a different kind of business model, the turnkey business model, where the controller vendor makes everything, does the firmware development and firmware validation, and the system validation and CJQ are done jointly by the controller vendor and the SSD maker. This is a shorter time to market. However, the SSD maker does not really own the code. So large OEMs and hyperscalers are a little unwilling to adapt SSDs with this business model. So FADU would like to change this business model a little bit to enable faster development and time to market. We'll develop the chip design and do the validation, and then the firmware development will start in parallel along with our chip validation, along with the SSD vendor. We'll do joint co-development on firmware validation, system validation, and CJQ for the first port. And the next port, based on the SSD vendor's comfort level, we're flexible. We can adopt this model, or they can go do everything themselves. This will enable us the shortest time to market, very efficient communication. The SSD maker can own the code as well as the SSDs. OEMs and hyperscalers can just hold the SSD vendor responsible for any problems that they see with the SSD. We think this change in business model will enable much faster time to market. So what we want you to remember today is FADU is the greatest SSD controller that's available today. Highest performance, lowest power, fastest time to market by basically enabling fast code changes as well as fast chip changes. And we've revved our business model to provide fastest SSDs. We are shipping in Gen 5 with WD's advanced line, and our Gen 6 is right around the corner in 2025. Thank you.